Everything you know about light is wrong. Right now, as you watch this video, light is traveling to your eyes, and you probably think it moves in straight lines. You've been told light has no mass, that it's pure energy, weightless. So how can gravity, which pulls on mass, affect something with zero mass? Here's the kicker. Light doesn't just feel gravity. Gravity can trap it completely. Black holes don't just pull on massive objects. They capture light itself. Light, the fastest thing in the universe, can be imprisoned. If light has no mass, how is this possible? This isn't science fiction. This is our universe breaking your assumptions about reality in the most profound way imaginable. By the end of this journey, you're going to understand something that challenged the greatest minds in physics for centuries. Something that rewrites the fabric of reality itself. And here's what will blow your mind. The answer changes everything you think you know about space, time, and the very ground beneath your feet. Before we dive in, hit that like button and subscribe, because you're about to take a journey that will fundamentally change how you see the universe. Drop a comment telling me what country you're watching from and what time it is for you right now. I love seeing this global community come together to explore the deepest mysteries of reality. Now, let's shatter some assumptions. Let's start with what seems like a simple question. What is light? You probably learned that light is electromagnetic radiation, that it travels at 299,792,458 meters per second in vacuum, that it behaves like both a wave and a particle. All true. But here's the first twist in our journey. Light is more strange than you ever imagined. In 1905, Albert Einstein published his paper on special relativity and revealed something shocking. From light's perspective, no time passes at all. A photon created at the beginning of the universe experiences its entire journey, billions of years to us, as a single timeless instant. The moment it's created and the moment it's absorbed happens simultaneously for the photon itself. Think about that. Light exists outside of time as we experience it. Now you might say, okay, but light still has no mass, right? Correct. A photon's rest mass is exactly zero. And this is where things get really interesting, because in 1687, Isaac Newton published his Principia Mathematica, laying out his law of universal gravitation. Every object with mass attracts every other object with mass. The force depends on the masses of the objects and the distance between them. It's proportional to the product of the masses and inversely proportional to the square of the distance. Simple, elegant, revolutionary. Newton's gravity works beautifully for planets, moons, apples falling from trees. But here's the problem. If gravity only pulls on mass and light has no mass, then light should be completely immune to gravity. It should travel in perfectly straight lines forever, unaffected by stars, planets, or anything else. For over 2 centuries, this seemed perfectly reasonable. No one had any reason to suspect otherwise. But in the early 1900s, cracks started appearing in Newton's beautiful edifice. Astronomers noticed something weird about Mercury's orbit. The planet was precessing its elliptical orbit, was rotating slightly faster than Newton's equations predicted. Only 43 arcseconds per century faster, but that tiny discrepancy was real and inexplicable. Something was wrong with gravity itself, and that something was about to change everything. Here's where our story takes a turn that seems almost too bizarre to be true. In 1907, while working as a patent clerk in Bern, Switzerland, Albert Einstein had what he later called the happiest thought of my life. He imagined a person falling off a roof. During the fall, the person wouldn't feel their own weight. They'd be weightless, just like astronauts in orbit. This simple thought experiment led Einstein to a profound realization. Gravity and acceleration are fundamentally the same thing. This is called the equivalence principle, and it's the seed from which general relativity grew. Think of it like this. Imagine you're in an elevator in deep space, far from any gravitational field. If someone starts accelerating that elevator upward at 9.8 meters per second squared, you'd feel pressed to the floor with exactly the same force you feel standing on Earth. There's no experiment you could do inside that elevator to tell whether you're accelerating in space or sitting still in Earth's gravity. They're equivalent. This isn't just similar, they're the same phenomenon. Now here's where it gets wild. If gravity and acceleration are the same thing, then anything affected by acceleration must also be affected by gravity. And light is definitely affected by acceleration. Imagine you're in that accelerating elevator in space, and someone shines a laser pointer horizontally across the elevator from one wall to the other. From inside the elevator, the light beam would appear to curve downward because the elevator is accelerating upward while the light crosses. The light starts at one height and ends at a lower relative height because the elevator is moved. But remember, acceleration and gravity are equivalent. So if light curves in an accelerating elevator, it must also curve in a gravitational field. Light must be affected by gravity. Not because light has mass, but because gravity isn't actually a force pulling on mass. Gravity is something far more profound. It's the curvature of spacetime itself. This is the moment where physics transforms from mechanics to geometry. Einstein spent 8 years wrestling with the mathematics, working with his friend Marcel Grossmann to master the tensor calculus needed to express his ideas. Finally, in November 1915, Einstein published the field equations of general relativity. These equations don't describe gravity as a force. They describe how mass and energy curve the fabric of spacetime, and how that curvature tells objects and light how to move. John Wheeler later summarized it perfectly. Spacetime tells matter how to move. Matter tells spacetime how to curve. But wait, you might be thinking, this sounds like philosophical speculation. How do we know spacetime is actually curved? How do we know light actually bends in gravitational fields? Great question. And here's what will blow your mind. We've tested it, measured it, photographed it, and the results confirm Einstein's predictions with stunning precision. Let me tell you about one of the most dramatic moments in the history of science. In 1919, just 4 years after Einstein published his equations, British astronomer Arthur Eddington organized an expedition to test general relativity. Einstein's equations predicted that light from distant stars would be bent when passing near the sun, and this bending would shift the apparent positions of stars. The effect would be tiny less than 2 arcseconds, but measurable. There was just one problem. You can't see stars near the sun when the sun is shining. You need a total solar eclipse. On May 29, 1919, there was a total solar eclipse visible from the island of Principe off the west coast of Africa and from Sobral in Brazil. Eddington led one expedition to Principe, while Andrew Cromlin led another to Brazil. During the 6 minutes of totality, when the moon completely blocked the sun, both teams photographed the stars around the sun's edge. Then they compared these positions to photographs taken at night, when the sun was nowhere near those same stars. The results were stunning. The stars had shifted by approximately 1.75 arcseconds, almost exactly matching Einstein's prediction. Newton's gravity predicted a shift too, but only half that amount, because in Newtonian physics, light has momentum, even without mass, and should be deflected slightly. Einstein's prediction was twice Newton's, because spacetime itself was curved. When the results were announced, it made front-page news around the world. The New York Times headline read, "Lights all askew in the heavens. Einstein theory triumphs." Overnight, Einstein became the most famous scientist on Earth. But here's the really mind-bending part. Eddington's experiment didn't just confirm that light bends. It confirmed that we live in a curved universe. Space and time aren't separate, absolute stages on which events happen. They're woven together into a 4-dimensional fabric that bends, stretches, and warps in the presence of mass and energy. Every massive object creates a dip in this fabric, like a bowling ball on a trampoline, and light follows the curves in spacetime, just as naturally as water flows downhill. Think of it like this. Imagine you're an ant walking on a giant sheet of rubber stretched flat. To you, moving in a straight line is easy. But now someone places a heavy sphere on the rubber, creating a deep depression. If you try to walk in what feels like a straight line near that depression, you'll actually curve around it, following the contour of the warped rubber. You're not being pulled by a force. You're just following the geometry. That's exactly what light does in curved spacetime. Light always takes the straightest possible path, but in curved spacetime, the straightest path is itself curved. This concept has a name, a geodesic. In flat space, a geodesic is a straight line. On the curved surface of Earth, geodesics are great circles, which is why planes fly in arcs when you look at a flat map. In curved spacetime, geodesics are the paths that light follows. So when we say light feels gravity, we're really saying light follows geodesics through curved spacetime. It's not being pulled. It's surfing the geometry of the universe itself. Now, I know what you're thinking. If this is true, we should be able to see more effects, more dramatic examples. And you're absolutely right. This is where our journey takes us into some of the most spectacular phenomena in the cosmos. What we're about to explore will make Eddington's eclipse experiment look like a simple parlor trick. The universe is full of examples where light's interaction with curved spacetime creates effects so dramatic, so visually stunning, that they seem impossible. Yet they're real, they're measurable, and they're opening windows into the deepest mysteries of existence. Are you ready for your mind to be blown? Because we're about to see how massive objects can turn spacetime itself into a lens, magnifying and distorting distant galaxies in ways that reveal invisible matter. We're going to discover how gravity can stretch time itself, making clocks run at different speeds depending on where you are. And we're going to confront the ultimate consequence of curved spacetime, regions where spacetime curves so severely that light itself cannot escape. But I'm getting ahead of myself. First, let me show you one of the most beautiful confirmations of Einstein's theory, gravitational lensing. Picture this. You're looking at a distant galaxy, billions of light years away. Between you and that galaxy lies another massive galaxy or cluster of galaxies. According to general relativity, the massive object in front should curve spacetime, and that curvature should bend the light from the distant galaxy behind it. The massive object acts like a lens, focusing and distorting the light from the background galaxy. This is called gravitational lensing, and it's one of the most spectacular visual confirmations of Einstein's theory. The first gravitational lens was discovered in 1979 by Dennis Walsh, Bob Carswell, and Ray Wayman. They were observing what they thought were two separate quasars, extremely bright, distant objects powered by supermassive black holes. The quasars were designated Q0957 plus 561a and b, and they were only about 6 arcseconds apart in the sky. But here's the weird part. The two quasars had nearly identical spectra and redshifts. They were at the same distance, had the same composition, the same properties. The odds of two such similar objects being so close together were astronomically small. Then they realized the truth. These weren't two quasars. They were two images of the same quasar, bent around an intervening galaxy by gravitational lensing. The galaxy's mass had curved spacetime so much that light from the single distant quasar took two different paths around it, creating two images. It was as if the universe had placed a magnifying glass in space, and we were seeing the same object twice. This was the first confirmed example of a phenomenon Einstein had predicted in 1936, though he thought it would be too rare to ever observe. Einstein was wrong about that. We've now found thousands of gravitational lenses. Some create multiple images of the same background object. Others create spectacular Einstein rings, complete circles of light surrounding the lensing galaxy, formed when the background source, the lens, and the observer are perfectly aligned. Still others create dramatic arcs and arclets, distorted and magnified images of distant galaxies stretched across the sky by the warping of spacetime. But here's what makes gravitational lensing so powerful. It lets us see things we couldn't see any other way. Remember how I mentioned dark matter? We can't see dark matter directly because it doesn't emit or absorb light. But dark matter has mass, and mass curves spacetime. So even though we can't see dark matter, we can see how it bends light from more distant galaxies. By studying the distortions in gravitational lensing, we can map the distribution of dark matter throughout the universe. We're using Einstein's prediction about light and gravity to detect matter that's otherwise completely invisible. Think of it like this. Imagine you're looking at a wall through a series of antique glass windows. The windows are wavy and distorted, but you can't see the glass itself. However, by carefully studying how the image of the wall is distorted, you could map out every imperfection in the glass. That's exactly what astronomers do with gravitational lensing. The glass is dark matter, and by studying how it distorts images of distant galaxies, we can figure out where the dark matter is and how much of it there is. One of the most famous examples is the bullet cluster, observed in detail in 2006. This is actually two galaxy clusters that collided and passed through each other. When they collided, the hot gas in each cluster interacted and slowed down, creating a shock wave visible in X-ray light. But the dark matter in each cluster passed right through with barely any interaction, because dark matter doesn't collide with normal matter or even with itself very much. By using gravitational lensing to map where the mass is, astronomers showed that most of the mass is not where the visible gas is, it's where the dark matter is. The lensing directly revealed the dark matter, separated from the normal matter. It's one of the most compelling pieces of evidence that dark matter is real. But gravitational lensing gives us even more than that. It lets us see farther back in time than we ever could otherwise. Distant galaxies are so faint that even our best telescopes struggle to see them. But if a massive galaxy cluster happens to lie between us and a distant galaxy, the cluster's gravity can magnify the light from that distant galaxy by factors of 10, 50, even 100 times. Suddenly, we can see galaxies that would otherwise be completely invisible. It's like nature has built cosmic telescopes for us, scattered throughout the universe. The Hubble Space Telescope and now the James Webb Space Telescope have used this technique to observe some of the most distant galaxies ever seen. Galaxies that formed less than 1 billion years after the Big Bang. Without gravitational lensing, these galaxies would be far too faint to study. But thanks to Einstein's prediction about how light interacts with curved spacetime, we can peer back to the cosmic dawn, watching the first galaxies form and evolve. We're using the geometry of the universe itself as our instrument. Now, here's where things get even weirder. Gravitational lensing doesn't just bend the path of light, it also affects the timing. Remember, spacetime is curved, not just space. Time is part of this geometry too. Light taking different paths around a gravitational lens doesn't just travel different distances. It also experiences different amounts of gravitational time dilation. This means light arriving along different paths reaches us at different times, even though it left the source simultaneously. In 2015, astronomers observed a spectacular example of this with a supernova nicknamed Refstal, after the Norwegian astronomer who predicted this possibility. This supernova appeared in a distant galaxy that was being gravitationally lensed by a massive galaxy cluster. The lensing created multiple images of the supernova, and Einstein's equations predicted that the light paths had different lengths and experienced different time delays. Sure enough, the supernova appeared in one position, then several months later appeared again in a different position, same explosion, different path, delayed arrival. They even predicted when a third image would appear, and it showed up right on schedule. The universe was rerunning the same cosmic explosion for us, with predictable delays, all because of how spacetime curves around massive objects. Think about how profound this is. The geometry of spacetime is so precisely understood that we can predict when light from an event will arrive at Earth via different paths, accounting for the curvature of space and the dilation of time. We're reading the ripples in the fabric of reality itself with incredible accuracy. This isn't speculation or philosophy. This is engineering-level precision in our understanding of how the universe works at its most fundamental level. But we haven't even gotten to the most extreme examples yet. Everything we've discussed so far involves relatively gentle curvatures of spacetime around galaxies and galaxy clusters. The deflection of light is small, measured in arcseconds or degrees at most. But what happens when spacetime curves more severely? What happens when you compress enough mass into a small enough volume that spacetime curves not just a little, but catastrophically? What happens when the geometry becomes so extreme that the usual rules break down? That's where we're going next, and it's going to challenge your understanding of reality at the deepest level. Before we continue, if you're enjoying this journey into the deepest mysteries of physics, make sure you're subscribed and hit that notification bell. We're just getting started, and what comes next is going to fundamentally change how you think about space, time, and the nature of reality itself. Drop a comment and let me know. Has your mind been blown yet? Because we're about to go even deeper. Now, let's talk about time. Not the time on your clock or your phone, the nature of time itself. Here's a question that sounds simple, but is actually profound. Does time flow at the same rate everywhere in the universe? You probably assume the answer is yes. 1 second is 1 second, whether you're on Earth, on Mars, or in the emptiest void between galaxies. But you'd be wrong. Spectacularly, demonstrably wrong. Time itself runs at different rates, depending on where you are in a gravitational field. This is called gravitational time dilation, and it's one of the most mind-bending predictions of general relativity. Here's the basic idea. The stronger the gravitational field you're in, or equivalently, the more curved spacetime is where you are, the slower time passes for you relative to someone in a weaker gravitational field. If you're standing on the surface of Earth, and I'm in orbit above you, time passes slightly faster for me than for you. We each experience time normally from our own perspective, but if we compare clocks later, mine will have ticked slightly more than yours. I will have aged slightly more than you. The difference is tiny for Earth's gravity, but it's real and measurable. Let me give you some numbers to make this concrete. The Global Positioning System GPS relies on satellites orbiting about 20,000 kilometers above Earth's surface. These satellites have atomic clocks that are incredibly precise. But because the satellites are in a weaker gravitational field than we are on Earth's surface, time runs faster for them, about 45 microseconds faster per day. That might not sound like much, but light travels about 30 centimeters in a nanosecond. If we didn't correct for gravitational time dilation, GPS would accumulate errors of several kilometers per day. Your navigation system works because engineers account for Einstein's prediction that time flows at different rates in different gravitational fields. Think of it like this. Imagine spacetime as a river flowing downhill toward massive objects. When you're deep in a gravitational field, you're in the faster, deeper part of the current. Time flows more slowly there, relative to the calmer, shallower water higher up. This isn't a perfect analogy. Spacetime doesn't actually flow like water, but it captures the essential idea that gravity affects the rate at which time passes. But here's where it connects back to light. Light has a frequency, which is effectively a clock. A photon oscillates, and the number of oscillations per second defines its color and energy. Blue light oscillates faster than red light. Now, imagine a photon climbing out of a gravitational field, say from the surface of a star to empty space far away. As the photon climbs, it's moving from a region where time runs slower to a region where time runs faster. From the perspective of an observer far from the star, the photon's oscillations appear to slow down, its frequency decreases, shifting toward the red end of the spectrum. This is called gravitational redshift, and it was first measured in a laboratory experiment by Robert Pound and Glenn Rebka at Harvard in 1959. They sent gamma rays up a 22.5-meter tower and measured their frequency at the top. Even over that tiny height difference, the gravitational field was slightly weaker at the top, and the gamma rays were redshifted by an amount exactly matching Einstein's prediction. More dramatically, we observe gravitational redshift in light from white dwarf stars, incredibly dense objects where gravity is strong enough to produce a noticeable shift in the spectrum of light. Now, let's connect this to what we discussed earlier about light bending and gravitational fields. Both phenomena, the bending of light and gravitational time dilation, come from the same source, the curvature of spacetime. In fact, you can think of light bending as a consequence of light always traveling at the same speed locally, but taking different amounts of coordinate time to cross different regions of space. Light takes the path of shortest proper time, which in curved spacetime means following a curved geodesic. Here's an analogy that might help. Imagine you're driving on a highway, and you always drive at exactly 100 kilometers per hour. That's the law, and you follow it precisely. But different lanes of the highway are moving. A right lane is on a conveyor belt moving forward, and the left lane is on a conveyor belt moving backward. If you want to go straight, you'd naturally drift toward the lane with the forward-moving conveyor, because even though your speedometer reads 100 kilometers per hour in your reference frame, your path curves relative to the fixed ground. Light does something similar in curved spacetime. It always moves at c locally, but the conveyor belt of spacetime itself is warped, so the path curves. This brings us to one of the most spectacular predictions of general relativity: frame dragging, also known as the Lenz-Thirring effect, after the two physicists who first described it in 1918, Joseph Lenz and Hans Thirring realized that rotating masses don't just curve spacetime, they drag it around with them, like a spinning ball in honey drags the honey around. Earth, as it rotates, drags spacetime around with it very slightly. If you could put a gyroscope in orbit around Earth and wait long enough, the gyroscope's axis would slowly presses, is not because anything is pushing on it, but because spacetime itself is being twisted by Earth's rotation. This effect is incredibly tiny for Earth, but in 2004, NASA launched Gravity Probe B specifically to measure it. The satellite carried 4 ultra-precise gyroscopes, the most perfect spheres ever manufactured, with surfaces smooth to within 40 atoms. Over a year of observations, the gyroscope's axis shifted by about 39 milliseconds per year due to frame dragging, matching Einstein's prediction within experimental error. Spacetime is not just curved, it can be twisted. The geometry of the universe is even stranger than we thought. But frame dragging becomes truly dramatic around rapidly rotating black holes, which we'll get to shortly. For now, let's talk about another consequence of gravitational time dilation that affects light in a profound way. If time itself slows down in stronger gravitational fields, and light is a wave with a frequency, then the wavelength of light must be affected by gravity. This has a bizarre consequence. The speed of light, when measured from far away, appears to slow down near massive objects. Wait, what? Didn't I say earlier that light always travels at c, the speed of light in vacuum, 299,792,458 meters per second exactly? Yes, and that's still true locally. If you're near a massive object and you measure the speed of light right where you are, you'll always get c. But if I'm far away watching you, and I use my rulers and clocks to measure how fast light is moving near you, I'll calculate a speed less than c. This isn't because light is actually slowing down. It's because your time is running slower and your space is contracted from my perspective. The speed of light is constant locally, but variable coordinately, depending on the curvature of spacetime. Think of it like this. Imagine you're watching a movie, and someone starts messing with the playback speed, slowing it down gradually. The characters in the movie don't notice anything from their perspective. Everything is normal. But you, watching from outside, see them moving in slow motion. That's analogous to what happens with light in a gravitational field. From the perspective of someone far away, light near a massive object appears to move more slowly, take longer to cover distances, and experience a stretched-out journey. But locally, nothing seems different. This has profound implications. It means that light's journey through the universe is not just a matter of traveling through space. It's traveling through spacetime, and the geometry of that spacetime determines everything about the journey. The path, the duration, the frequency, even the apparent speed. Light is not just a messenger bringing us information from distant objects. It's a probe of the geometry of spacetime itself. Every photon that reaches your eye has a story encoded in it about the spacetime it traveled through. In 2020, astronomers using the European Southern Observatory's Very Large Telescope observed something extraordinary. A star orbiting extremely close to the supermassive black hole at the center of our Milky Way galaxy. This star, called S2, reached speeds of about 3% of the speed of light at its closest approach. The team, led by Reinhard Genzel, detected both gravitational redshift and relativistic effects in the star's light, confirming Einstein's predictions in one of the strongest gravitational fields we can observe. Genzel shared the 2020 Nobel Prize in Physics for this work, continuing the tradition of testing general relativity in increasingly extreme conditions. Now, I want you to pause and think about what we've covered so far. Light, despite having no mass, is profoundly affected by gravity. Not because gravity pulls on it, but because light follows geodesics through curved spacetime, and massive objects curve spacetime. This curvature bends light's path, creates gravitational lenses that magnify distant galaxies, causes time to run at different rates, redshifts light climbing out of gravitational fields, and even allows rotating masses to drag spacetime around with them. Every single one of these effects has been measured, confirmed, and is now used in practical applications, from GPS to astronomy. But we're about to go to the extreme. We're about to explore what happens when spacetime curves so much that it breaks, when the geometry becomes so warped that not even light, the fastest thing in the universe, can escape. We're going to talk about black holes, and what I'm about to tell you will challenge everything you think you know about the nature of reality, the meaning of time, and what can and cannot exist in our universe. This is where Einstein's elegant equations lead to their most dramatic, most disturbing, and most beautiful conclusion. Are you ready? Because there's no turning back from here. Let me ask you a question. What is the most destructive object in the universe? A supernova? A gamma-ray burst? How about this? What if I told you there are objects so extreme, so violent in their distortion of reality, that they literally tear holes in spacetime itself? Objects where the curvature becomes infinite, where time stops, where the very equations we've been using to understand the universe break down and scream infinities at us? These objects exist. They're called black holes, and they represent the ultimate consequence of light's interaction with gravity. Here's the basic idea, and it's going to sound like science fiction, but it's absolutely real. If you compress enough mass into a small enough volume, space-time curves so severely that it creates a point of no return. Get closer than this critical distance called the event horizon, and escape becomes literally impossible. Not impractical, not difficult, impossible. The geodesics of spacetime all point inward. There are no outward paths. Not for spaceships, not for particles, not even for light itself. This critical distance is called the Schwarzschild radius, named after Karl Schwarzschild, who found the first exact solution to Einstein's field equations in 1915, just weeks after Einstein published them. Schwarzschild was serving in the German army on the Eastern Front during World War I, and he worked out the mathematics between artillery barrages. Tragically, he died just a few months later from a disease he contracted in the trenches, but his solution revealed something astonishing. If you compress any mass inside its Schwarzschild radius, you create an event horizon. The formula is beautifully simple. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For Earth, the Schwarzschild radius is about 9 millimeters. If you could compress all of Earth's mass into a sphere smaller than a marble, it would become a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with 1,000,000 times the Sun's mass, like the one at the center of our galaxy, the Schwarzschild radius is about 3 million kilometers, roughly 4 times the distance from Earth to the Moon. Now, here's what happens to light near a black hole, and this is where things get truly wild. Far from the black hole, light behaves normally, following slightly curved geodesics. But as light gets closer, the curvature intensifies. At a distance of 1.5 times, the Schwarzschild radius, a region called the photon sphere spacetime, is so curved that light can orbit the black hole in a circular path. A photon at this distance, aimed tangentially, will circle the black hole forever, neither escaping nor falling in. If you could somehow position yourself at the photon sphere and look forward, you'd see the back of your own head, your image having circled the entire black hole. But the photon sphere is unstable. Nudge the photon slightly inward, and it spirals into the event horizon. Nudge it slightly outward, and it escapes to infinity. This is the last place where light has a choice. Inside the photon sphere, escape is still possible, but the paths narrow. And at the event horizon itself, all paths point inward. The future direction of time and the inward direction toward the singularity become the same thing. Think about what this means. At the event horizon, space-time is so curved that the future for anything crossing that boundary necessarily involves moving toward the center of the black hole. You can no more avoid reaching the singularity once you've crossed the event horizon than you can avoid reaching next Tuesday. It's not a matter of thrust or speed. It's a matter of geometry. The very structure of space-time has changed such that inward and forward in time are aligned. Escaping would require moving backward in time, which is impossible. And here's the kicker. Once light crosses the event horizon, it's gone. Not hidden, gone from the universe outside the black hole. The event horizon is a one-way membrane in space-time. Information, matter, energy, light all can go in, but nothing comes out. This is why we call them black holes. They're not just dark objects that don't emit light. They're regions of space-time that have separated themselves from the rest of the universe. They're tears in the fabric of reality. But wait, there's more, and it's even weirder. From the perspective of someone falling into a black hole, crossing the event horizon is actually not that dramatic. There's no wall, no barrier, no sign that says, event horizon, no U-turns. If the black hole is large enough, you wouldn't even feel any tidal forces at the horizon. You'd just cross over, likely without even noticing it first. Time would continue to flow forward for you normally. You'd see the universe outside getting brighter and compressed into a shrinking circle behind you as you fell. But from the perspective of someone watching you fall in from far away, something very different happens. As you approach the event horizon, gravitational time dilation becomes more and more extreme. Your clock appears to run slower and slower. The light from you becomes more and more redshifted. You appear to slow down, approach the horizon asymptotically, and fade away. To the outside observer, you never actually cross the horizon. You just get frozen there, your image slowly dimming to invisibility. But from your perspective, you cross it without hesitation and continue falling inward. This is one of the most profound insights of general relativity. Different observers can have fundamentally different perspectives on what happens in curved spacetime, and both perspectives are valid. You really do cross the horizon from your perspective. You really don't cross it from the outside observer's perspective. Both are true. Spacetime is relative in ways that make time travel stories seem simple by comparison. Now, you might be wondering, If nothing can escape a black hole, how do we know they exist? Great question. We can't see the black holes themselves, but we can see their effects. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together, released the first image of a black hole's shadow. The target was the supermassive black hole at the center of the galaxy M87, about 55 million light-years away, with a mass of about 6.5 billion suns. The image shows a dark shadow surrounded by a bright ring of light-hot gas swirling around the black hole, some of it escaping and some of it falling in, heated to billions of degrees. The shadow is larger than the event horizon itself because of light bending. Photons aimed to just miss the event horizon get deflected by the extreme curvature, creating a larger dark region. The size and shape of that shadow exactly match the predictions of general relativity. In 2022, the Event Horizon Telescope released a similar image of Sagittarius A*, the supermassive black hole at the center of our own Milky Way galaxy, about 27,000 light-years from Earth. These images are direct visual evidence that black holes exist and that space-time behaves exactly as Einstein predicted. But detecting black holes goes back much further. In the 1970s, astronomers discovered X-ray sources in binary star systems where a visible star orbits an invisible companion. The X-rays come from an accretion disk matter from the visible star being torn away by the gravitational field of the invisible companion and spiraling inward, heating up to millions of degrees. By measuring the orbit of the visible star, astronomers can calculate the mass of the invisible companion. In many cases, that mass exceeds the theoretical maximum for a neutron star, about 3 solar masses. The only explanation is a black hole. Cygnus X1, discovered in 1964 and confirmed as a black hole in the 1970s, was the first such object. Since then, we found dozens of stellar mass black holes in our galaxy through similar techniques. And at the centers of most large galaxies, including our own, we found supermassive black holes ranging from millions to billions of solar masses. These monsters are detected by watching stars orbit around the invisible mass concentrations, by observing jets of matter blasted away from the accretion disks, and now by direct imaging of their shadows. But here's what will blow your mind. In 2015, we detected black holes in an entirely new way through gravitational waves. When two black holes orbit each other, they stir up spacetime, creating ripples that propagate outward at the speed of light. These are gravitational waves, predicted by Einstein in 1916, but not directly detected until a century later. On September 14, 2015, the LIGO detectors in Louisiana and Washington simultaneously detected a signal. Two black holes, each about 30 times the mass of the Sun, had spiraled together and merged about 1.3 billion years ago. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting as light at that moment. Think about that. The geometry of space-time itself was oscillating, stretching and compressing in a wave that crossed the universe and passed through Earth. LIGO detected it by measuring changes in distance, less than 1,000th, the width of a proton. This wasn't light carrying information about black holes. This was space-time itself vibrating, ringing like a bell from the most violent collision imaginable. Rainer Weiss, Barry Barish, and Kip Thorne shared the 2017 Nobel Prize in Physics for this discovery. Since then, LIGO and its partner detector Virgo have detected dozens of black hole mergers, neutron star mergers, and even the merger of a black hole with a neutron star. We're listening to the universe in a completely new way, hearing the symphony of space-time as massive objects collide and merge. And every single detection confirms Einstein's predictions about how space-time curves, oscillates, and transmits information across cosmic distances. But let's return to light and black holes, because there's something even more extreme I need to tell you about. The black holes I've described so far are called Schwarzschild black holes non-rotating, perfectly spherical, defined solely by their mass. But real black holes aren't like that. Real black holes form from collapsing stars, and stars rotate. When a star collapses, conservation of angular momentum means the resulting black hole rotates extremely rapidly. These are called Kerr black holes, after Roy Kerr, who found the solution for rotating black holes in 1963. Rotating black holes are far stranger than non-rotating ones. The rotation drags spacetime around, with its frame dragging taken to the extreme. Close to a rotating black hole, spacetime itself is swirling around like water going down a drain. It's impossible to remain stationary. You're inevitably dragged around the black hole whether you like it or not. This region is called the ergosphere, and it exists outside the event horizon. Inside the ergosphere, you can still escape, but you can't avoid rotating. And here's where light does something absolutely bizarre. In the ergosphere, there are photon trajectories that gain energy from the black hole's rotation. If you drop something into the ergosphere at just the right angle, it can split into two pieces, one falling in and one escaping with more energy than the original object had. This is called the Penrose process, after Roger Penrose, who described it in 1969. You can extract energy from a black hole's rotation by carefully dropping matter into the ergosphere. Some scientists have speculated that advanced civilizations could use rotating black holes as ultimate power sources, extracting energy from the rotation until the black hole stops spinning. But it gets weirder. Deep inside the event horizon of a rotating black hole, the singularity, the point where density and curvature become infinite, isn't a point at all. It's a ring. And according to the mathematics, you could potentially pass through this ring singularity into another region of spacetime, maybe even another universe. These solutions to Einstein's equations include wormholes, closed time-like curves, and all manner of causality-violating pathways through spacetime. Now, do these exotic solutions represent real possibilities, or are they mathematical artifacts that nature prevents from forming? We don't know. Most physicists suspect that quantum mechanics, which we haven't incorporated into our discussion yet, will eliminate the most bizarre features. But the fact that Einstein's equations allow such possibilities shows just how strange spacetime can be when curvature becomes extreme. The universe is far weirder than our everyday experience suggests. Let me take a moment to connect this back to our original question. How can light feel gravity? By now, you understand the answer isn't simple. Light doesn't feel gravity as a force. Light follows geodesics through curved spacetime, and massive objects curve spacetime. In gentle curvatures, light bends slightly, creating gravitational lenses. In moderate curvatures, light experiences significant redshift and time dilation. In extreme curvatures, light can orbit in unstable paths. And in the most extreme curvatures inside a black hole's event horizon, light is trapped forever, unable to escape because every path through spacetime points inward. This is geometry, not force. This is the structure of reality itself, warped by energy and mass. And the fact that we've measured these effects, photographed them, detected them through gravitational waves, and used them for practical applications, like GPS, shows that this isn't abstract philosophy. This is how the universe works. This is reality. At this point, if you're still watching, your brain is probably hurting. And that's okay. That's normal. You're grappling with concepts that challenged the greatest minds of the 20th century. But here's what I want you to understand. This isn't magic. This is physics. This is the universe revealing its deepest secrets through careful observation, mathematical precision, and experimental verification. And we're not done yet. Not even close. Because there are implications of everything we've discussed that reach into your daily life, into the nature of existence, and into questions about the ultimate fate of the universe. That's where we're going next, and it's going to tie everything together in a way that will change how you see reality forever. Make sure to hit that like button if you're still with me, and drop a comment telling me what part has blown your mind the most so far. Are you ready to see how all of this connects to you, to your life, to the meaning of existence? Then let's continue this journey together. Now, let's bring this down to Earth literally. Everything I've told you about light, gravity, space-time curvature, black holes, it all sounds very cosmic, very distant, very removed from your daily life. But here's the truth that's going to shake you. You are living in curved space-time right now. You are experiencing gravitational time dilation at this very moment. The ground beneath your feet isn't solid in the way you think it is. It's a region of warped geometry, and your entire existence is shaped by this curvature in ways you've never imagined. Let me make this personal. Right now, as you watch this video, you're probably sitting or standing somewhere on Earth. Maybe you're at sea level. Maybe you're on a mountain. Maybe you're in an airplane. Here's what's happening. Your body is composed of atoms, and those atoms are following geodesics through curved spacetime. You feel weight, not because Earth is pulling you down with a force, but because Earth's mass curves spacetime, and you're trying to follow a geodesic through that curved spacetime. But the ground prevents you from following the geodesic. It pushes up on you, and you feel that push as weight. Think about it differently. If you were in free fall, say, in the International Space Station orbiting Earth, you'd be weightless. Not because there's no gravity. Earth's gravity at the ISS altitude is about 90% as strong as at the surface. But because you'd be following a geodesic through curved spacetime without anything blocking your path. The astronauts in the ISS aren't escaping gravity. They're falling around Earth on a geodesic, and it feels like zero gravity because nothing is pushing on them. They're in constant free fall. You, on the other hand, are being prevented from following your natural geodesic by the electromagnetic forces in the ground pushing up on you. You interpret this as the ground is solid and stationary, and gravity is pulling me down. But the reality is that you're trying to fall through curved spacetime, and the ground is accelerating you upward relative to the geodesic you want to follow. This is Einstein's equivalence principle in action. Being stationary in a gravitational field is equivalent to being accelerated. You're being accelerated upward by the ground at about 9.8 meters per second squared, and you feel this as weight. Now, here's where it connects to time. Because you're deep in Earth's gravitational field, at the bottom of the space-time curvature created by Earth's, mass time runs slightly slower for you than it does for someone higher up. If you have an identical twin, and they spend their life living on a mountaintop while you live at sea level, they will age slightly faster than you. Over a 79-year lifetime, the difference would be about 90 microseconds. Tiny, but real. This is constantly happening. GPS satellites experience time 45 microseconds per day faster than we do. The International Space Station experiences time about 8 microseconds per day faster. Even the top of your head ages slightly faster than your feet, about 10 to 16 seconds per second faster. Over your entire lifetime, the top of your head ages about 100 nanoseconds more than your feet. This sounds absurd, but it's measurable and true. Your head is literally older than your feet because time flows at different rates depending on how deep you are in Earth's gravitational well. Think of it like this. You're at the bottom of an ocean of curved spacetime, and the pressure down here makes your clock tick slightly slower than clocks higher up. Every photon climbing out of Earth's gravitational field gets redshifted. Every physical process runs slightly slower for you than it does for someone in orbit. You're living in slow motion compared to someone far from any gravitational field, but you don't notice because everything around you, your thoughts, your heartbeat, your clocks, are all slowed by the same factor. But here's what really blows my mind, and I hope it blows yours too. This means that the history of the universe has unfolded at different rates in different locations. Near the event horizon of a black hole, time is so dilated that an outside observer sees you frozen, taking infinite time to cross. But for you, time flows normally. This means that the age of the universe 13.8 billion years is measured in a specific reference frame. For something near a black hole, far less time may have passed. For something far from all gravitational fields, more time may have passed. The universe doesn't have a single universal clock. Time is local, relative, woven into the fabric of spacetime in a way that makes every observer's experience unique. And light, in its journey across the cosmos, carries information about all the spacetime it has traveled through, the curvatures, the time dilations, the redshifts and blueshifts. Every photon that reaches your eye is a messenger from a specific path through spacetime, and its properties tell you about the geometry it traversed. Now, let's zoom out even further and think about the universe as a whole. General relativity doesn't just describe gravity around planets and stars. It describes the entire universe. In 1922, Alexander Friedmann found solutions to Einstein's equations describing a universe that could expand or contract. In 1927, Georges Lemaitre independently found similar solutions and proposed that the universe began in a hot, dense state, what we now call the Big Bang. In 1929, Edwin Hubble observed that distant galaxies are moving away from us with velocities proportional to their distances, confirming that the universe is expanding. But here's the wild part. The expansion of the universe isn't galaxies moving through space. It's space itself expanding. The fabric of spacetime is stretching, carrying galaxies along with it. This has profound consequences for light. When light travels from a distant galaxy to us through expanding spacetime, its wavelength gets stretched along with the expansion of space. By the time the light reaches us, it's been redshifted, not just by gravity, but by the expansion of the universe itself. This is called cosmological redshift, and it's different from both Doppler redshift and gravitational redshift, though related to both. The most distant objects we can see, galaxies near the edge of the observable universe, have cosmological redshifts so large that light that was emitted as ultraviolet is received as infrared. The universe has expanded so much during the light's journey that wavelengths have been stretched by factors of 10 or more. And here's the kicker. Some of these distant galaxies are now receding from us faster than the speed of light, because space itself is expanding faster than light can cross it. This doesn't violate special relativity. Nothing is moving through space faster than light. But space itself can expand faster than light, carrying distant objects beyond our ability to ever reach them, even at the speed of light. This brings us to one of the most profound discoveries in modern cosmology: dark energy. In 1998, two teams of astronomers studying distant supernova discovered something shocking. The expansion of the universe isn't slowing down due to gravity, as everyone expected. It's speeding up. Something is pushing space itself to expand faster and faster. We call this something dark energy, and it makes up about 68% of the total energy density of the universe. We don't know what it is. It might be a property of empty space itself, a cosmological constant, as Einstein once proposed. It might be a new field permeating the universe. We don't know. But here's what it means for light and spacetime. The universe's expansion is accelerating, which means that distant objects are receding from us faster and faster. Eventually, trillions of years from now, the expansion will carry distant galaxies beyond the cosmic horizon, the distance beyond which light can never reach us no matter how long we wait. The observable universe will shrink, in a sense. Future civilizations will live in a darker cosmos, able to see fewer and fewer galaxies, with less and less evidence that the universe extends beyond their local neighborhood. Think about the implications. We live in a special time in cosmic history when we can observe distant galaxies, study the cosmic microwave background, and learn about the Big Bang. If we'd evolved trillions of years from now, we wouldn't be able to see most of the universe. We'd have no evidence of the Big Bang, no way to learn cosmology. The universe would appear much smaller and less knowable. We're lucky to exist when we do, able to look back across billions of light years and billions of years of time, learning the history and structure of the cosmos. And light is our only window to this knowledge. Every photon carries information encoded in its wavelength, its polarization, its direction, its timing. By studying light, how it bends around galaxies, how it's redshifted by expanding space, how it's absorbed by intervening gas clouds, we've reconstructed the entire history of the universe from the Big Bang to the present. We know the universe is 13.8 billion years old. We know it's been expanding and accelerating. We know it's composed of ordinary matter, and dark energy in specific proportions, all from studying light. But there's another profound connection I want to make. Everything in the universe, every atom in your body, every molecule of air you breathe, was forged in stars and stellar explosions billions of years ago. Carl Sagan famously said, "We are made of star stuff," and it's literally true. The carbon, oxygen, nitrogen, iron, calcium in your bones, all of it was created by nuclear fusion in stars and dispersed into space when those stars died. You are the universe contemplating itself. And the process that allowed this to happen, the formation of atoms, molecules, planets, life, all depended on light and its interaction with matter. In the first 380,000 years after the Big Bang, the universe was opaque. It was so hot and dense that photons couldn't travel far before interacting with free electrons. Light was trapped, scattered endlessly. But as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons could travel freely. The universe became transparent, and light could propagate across cosmic distances. This moment is called recombination, and the light released at that moment has been traveling through space ever since. We observe it today as the cosmic microwave background radiation, the afterglow of the Big Bang. That light, ancient, redshifted from visible wavelengths to microwaves by the expansion of space, is the oldest light in the universe. It carries information about the temperature, density, and composition of the universe when it was just 380,000 years old. By studying tiny variations in this light, hot spots and cold spots differing by only millionths of a degree, we've learned how galaxies formed, how the universe evolved, what dark matter does, and what the ultimate fate of the universe might be. Here's where it all comes together. Light interacts with gravity, not because of a force, but because gravity is the curvature of spacetime, and light follows geodesics through that curvature. This simple principle explains everything from why GPS needs relativity corrections to why black holes are black, to how we know the universe is expanding and accelerating. It connects the smallest scales, photons oscillating, to the largest scales, the structure and evolution of the entire cosmos. And you are part of this story. The atoms in your body were forged in stars, dispersed by supernova, and reassembled on a planet orbiting a younger star. You exist in a bubble of curved spacetime, experiencing time dilation, living at the bottom of a gravitational well. The light entering your eyes right now has traveled through curved spacetime, carrying information about the objects and processes that emitted it. You're not separate from the universe. You're a pattern in the fabric of spacetime, a temporary arrangement of matter and energy, intimately connected to everything around you through the curvature of space and time. This isn't poetry. This is physics. This is how reality works at its most fundamental level. And understanding it, really grasping how light, gravity, spacetime, and the universe fit together, gives you a perspective that transforms how you see everything. You're not just a person on a planet. You're a conscious pattern emerging from the geometry of spacetime, made of atoms forged in stellar furnaces, contemplating the very fabric of reality that gives rise to your existence. If that doesn't blow your mind, I don't know what will. Take a moment, let this sink in. You are part of something vast, ancient, and beautiful, a cosmos governed by elegant mathematical principles that we've managed to decode through centuries of careful observation and brilliant insight. Before we move to our final sections, Pause and hit that like button if this journey has changed your perspective. Comment and tell me, how do you feel knowing that you're living in curved spacetime right now? That your head is older than your feet? That the ground beneath you is accelerating you through geometry itself? Let's share this moment of cosmic wonder together. Now, let's address something that might be bothering you. We've talked a lot about general relativity, about curved spacetime, about how light follows geodesics. But there's another fundamental theory of physics, quantum mechanics, and it describes reality very differently. In quantum mechanics, light is made of particles called photons, and those photons have properties like energy and momentum, even though they have zero rest mass. So how do these two descriptions fit together? And here's the unsettling truth. They don't, not completely. And this gap in our understanding points to one of the deepest mysteries in physics. Let's start with what we know. In quantum mechanics, light is quantized into discrete packets called photons. Each photon has an energy proportional to its frequency E equals h times frequency, where h is Planck's constant. Even though photons have zero rest mass, they have momentum P equals E divided by C. This momentum is real and measurable. When photons strike a surface, they exert radiation pressure. In fact, there are proposals to use powerful lasers or solar sails to push spacecraft, using the momentum of photons as a propulsion method. Now, here's where it gets interesting. If photons have momentum, you might think that's why gravity affects them. Gravity pulls on the momentum, not the mass. But that's not quite right either. In general relativity, gravity doesn't pull on anything. Gravity is curvature, and photons follow geodesics. The momentum of the photon is related to its energy, which in turn contributes to the stress energy tensor, the mathematical object that tells spacetime how to curve. So photons, despite having no mass, do contribute to the curvature of spacetime because they carry energy. In fact, light itself can theoretically create a black hole. If you could somehow concentrate enough light into a small enough region, we're talking about intensities far beyond anything we can achieve, the light's energy would curve spacetime so much that it would create an event horizon. These hypothetical objects are called Kugelblitz black holes, from the German word for ball lightning. They're purely theoretical. You'd need to focus so much energy into such a tiny space that it's beyond any current technology, but the equations allow it. Energy curves spacetime, and light is energy. But here's the problem. Quantum mechanics and general relativity are fundamentally incompatible in certain regimes. General relativity is a classical theory, meaning it describes smooth, continuous spacetime. Quantum mechanics is, well, quantum discrete, probabilistic, fundamentally uncertain. When you try to apply quantum mechanics to gravity or general relativity to subatomic scales, you get nonsensical results. Infinities crop up in the equations. Predictions break down. This is most apparent at the center of black holes. General relativity predicts a singularity, a point of infinite density and infinite curvature. But infinite is code for our theory as broken down here. Most physicists believe that quantum effects, which we don't yet understand, smooth out the singularity into something finite but extremely dense and curved. We just don't know what the correct description is. Similarly, at the moment of the Big Bang, general relativity predicts a singularity infinite temperature, infinite density. But again, this is where quantum mechanics should take over. The very early universe was so small and so dense that quantum effects dominated. Understanding what happened in the first tiny fraction of a second the Planck time, about 10 to 43 seconds, requires a theory of quantum gravity that we don't yet have. There are candidates for such a theory. String theory proposes that fundamental particles, including photons, are actually tiny vibrating strings. Different vibration modes correspond to different particles. In string theory, gravity emerges naturally from one particular vibration mode. The graviton, a hypothetical quantum particle that mediates the gravitational interaction. But string theory requires extra dimensions of space beyond the three we experience, and it hasn't yet made testable predictions that distinguish it from other theories. Loop quantum gravity is another approach. It proposes that spacetime itself is quantized at the smallest scales, that there's a smallest possible unit of space and time, beyond which the concepts don't make sense. In this view, spacetime is woven from discrete loops, and the smooth geometry of general relativity is an approximation that emerges at larger scales. Loop quantum gravity suggests that singularities don't exist. When you zoom in far enough, spacetime becomes discrete and finite. But here's the honest truth. We don't know which, if any, of these approaches is correct. We don't have a complete theory of quantum gravity. We don't fully understand how light, spacetime, and quantum mechanics fit together at the most fundamental level. And this is actually exciting, not discouraging. It means there are still profound mysteries to uncover, Nobel Prizes to be won, revolutions in our understanding waiting to happen. But even without a complete quantum gravity theory, we can say some things. In the regime where general relativity works, anything larger than atomic scales and less extreme than black hole singularities, or the Big Bang light follows geodesics through curved spacetime. This is experimentally confirmed. In the regime where quantum mechanics works atomic and subatomic scales without extreme gravity, light behaves as quantized photons. This is also experimentally confirmed. The problem is only when you try to combine both at once in the most extreme conditions. For the vast majority of the universe, including everything we've discussed in this video, general relativity works perfectly. The bending of light around stars and galaxies, gravitational lensing, time dilation, black holes, all of this is described accurately by Einstein's equations without needing quantum mechanics. The quantum nature of light becomes important when we talk about how light is emitted and absorbed by atoms, how it interacts with matter at small scales, but the propagation of light through spacetime, the paths it takes, the way it's affected by gravity, that's all classical general relativity. So to answer our original question from a quantum perspective, how can light feel gravity if light is photons, and photons have no mass? The answer is the same. Gravity isn't a force pulling on mass. Gravity is the curvature of spacetime, and photons, like everything else, follow geodesics through that curvature. The fact that photons have energy and momentum means they also contribute to the curvature. They're part of the stress-energy tensor, but they're affected by the curvature regardless of their quantum properties. The quantum and classical descriptions agree in the regimes where both apply. There's something beautiful and humbling about this. We've achieved an incredible understanding of the universe, building two monumental theories, quantum mechanics and general relativity, that between them explain almost everything we observe. Yet we know these theories are incomplete. We know there are realms where they clash, where our understanding breaks down. And that's okay. Science isn't about having all the answers. It's about asking the right questions, building theories that work, testing them, and continually refining our understanding. Here's what you should take away from this. The universe operates according to principles that we've decoded through observation, experimentation, and mathematical reasoning. General relativity tells us that gravity is the curvature of spacetime, and light follows geodesics through that curvature. Quantum mechanics tells us that light is made of photons with discrete energies and momenta. Both descriptions are correct in their domains, and where they overlap, we have work to do. But the big picture of the story I've been telling you throughout this video is rock solid. Light interacts with gravity because gravity is geometry, not force. Spacetime is curved by mass and energy. Light follows the curvature. This explains everything from why your GPS works, to why black holes are black, to how we know the universe is expanding. It's one of humanity's greatest intellectual achievements, and you now understand it at a deep level. Now, we're approaching the end of our journey together, but I want to leave you with something profound. We've talked about physics, mathematics, observations, experiments. But there's a human dimension to all of this that I don't want to overlook. This understanding didn't come from a single genius working in isolation. It came from centuries of people asking questions, making observations, challenging assumptions, building on each other's work, and gradually assembling a picture of reality more strange and beautiful than anyone imagined. Isaac Newton gave us the first mathematical description of gravity in the 1680s. For over 2 centuries. So here's my challenge to you. Take what you've learned and share it. Talk to your friends about how light follows curved geodesics. Explain to someone why GPS needs relativity corrections. Look up at the night sky and realize that the starlight entering your eyes has traveled across curved spacetime, redshifted by expansion, carrying ancient information about the universe. Let this knowledge change how you see the world. Because understanding is a form of power. Not power over others, but power over ignorance, fear, and small-mindedness. When you understand how the universe works, really understand it, not just memorize facts, you become part of something larger. You connect with every human who has ever looked up at the stars and wondered. You honor the centuries of work that went into building this knowledge. And you position yourself to contribute, in whatever way you can, to the ongoing project of understanding reality. Maybe you'll become a physicist and work on quantum gravity. Maybe you'll be an engineer designing the next generation of gravitational wave detectors. Maybe you'll be a teacher, inspiring the next generation to ask questions. Or maybe you'll just be someone who looks at the universe with a sense of wonder and appreciation, knowing that you're part of this magnificent cosmos made of star stuff, living in curved spacetime, experiencing the universe contemplating itself. And that's enough. That's beautiful. That's significant. So as we wrap up this journey, I want to thank you. Thank you for spending over 3 hours with me, exploring one of the deepest questions in physics. Thank you for challenging your assumptions, following the logic, and embracing the strangeness of reality. Thank you for being curious. The universe needs more curious people. Hit that like button one more time to celebrate what you've learned. Subscribe if you want more content like this, explorations of deep questions that change how you see reality. And drop a comment telling me, what will you do with this knowledge? How has this changed your perspective? What questions do you have now? Remember, the universe is not only stranger than we imagine, it's stranger than we can imagine. But with patience, curiosity, and the willingness to follow where the evidence leads, we can decode its deepest mysteries. We can understand how light feels gravity, how space-time curves, how black holes form, how the universe began, and how it will end. And in understanding these things, we understand ourselves. We understand our place in the cosmos. We understand that we are not separate from the universe. We are expressions of it, temporary patterns in the fabric of space-time, conscious beings capable of comprehending the very laws that govern our existence. That is the gift of science. That is the power of understanding. And that is why questions like, how can light feel gravity, are worth asking, worth exploring, worth spending 3.5 hours explaining in detail. Because the answer, light, follows geodesics through curved spacetime, is more than just physics. It's a doorway into understanding reality at its deepest level. It's a reminder that the universe operates according to principles more elegant and beautiful than we might have guessed. And it's an invitation to keep asking questions, keep exploring, keep learning. The universe is waiting. It has more secrets to reveal, more mysteries to solve, more mind-blowing truths to discover. And with the foundation you've built today, understanding how light interacts with gravity, how space-time curves, how the cosmos evolves, you're better equipped than ever to continue that journey. So go forth with wonder. Look at the world with new eyes. Question your assumptions. Embrace the strangeness of reality. And never stop learning. Thank you for joining me on this journey. Until next time, keep looking up, keep asking questions, and keep marveling at the magnificent universe we're privileged to inhabit. This has been 3.5 hours exploring how light can feel gravity from the basic principles to the most extreme implications, from GPS satellites to black holes, from the beginning of the universe to your own body, experiencing time dilation right now. You've learned about geodesics and gravitational lensing, about time dilation and gravitational waves, about Einstein and Eddington, and hundreds of years of human ingenuity dedicated to understanding reality. And the most important thing? You've learned that reality is stranger, more beautiful, and more comprehensible than you might have thought. Science isn't about memorizing facts. It's about building understanding, making connections, and seeing how everything fits together into a coherent picture. You now have that picture. You understand something profound about the universe. And that understanding is yours forever. Use it well. Thank you. And remember, the universe is not only stranger than we imagine, it's stranger than we can imagine. But we can still understand it, one question at a time.